This is a sound chip from 1982. It cost the company that made it $4. A tested one now sells for somewhere between 60 euros and 100 pounds, depending on the revision, which is more than the entire computer it was designed for cost by 1985. It also has a design flaw its own creator predicted in writing before it shipped. That flaw is the reason people still buy the physical chip instead of emulating it. Bob Yanez joined MOS Technology in 1979, 2 years out of Villanova. He was 24 when he started work on the sound chip, and 25 when the Commodore 64 shipped. He had already built the machine that became the VIC-20 at home on a spare prototype board, unasked. IEEE Spectrum describes him as the sound chip designer and systems architect of the Commodore 64, and Yanez says of the C64, in passing, which I also designed. His engineering creed, from a 1985 interview, dates to being a broke high school student scavenging parts to build a synthesizer. Anytime I design something, I want to use the minimum number of components possible. It's a personal challenge. If there's a spare gate in a gate package, I'll work to get rid of the entire package. And this is the thing to understand before anything else. He was not trying to make a computer beep. From his own account in 1996, when I designed the SID chip, I was attempting to create a single-chip synthesizer voice which hopefully would find its way into polyphonic, polytimbral synthesizers. And on the competition, I thought the sound chips on the market, including those in the Atari computers, were primitive and obviously had been designed by people who knew nothing about music. He is specific about what they got wrong. With most of the sound effects in games, there is either full volume or no volume at all. That really makes music impossible. There's no way to simulate the sound of any instrument, even vaguely with that kind of envelope, except maybe an organ. Then dryly, it took a long time for people to understand this. MOS Technology was a merchant semiconductor house. It sold chips to other companies. Yanez's plan was to sell the SID to synthesizer manufacturers, and he says Sequential Circuits was interested at one point, but nothing came of it. The Commodore 64 consumed the entire supply. By the time chips were readily available, he had left the company. The chip was not designed for a computer. Albert Charpentier, who ran the LSI group, put it plainly, we were fresh out of ideas for whatever chips the rest of the world might want us to do, so we decided to produce state-of-the-art video and sound chips for the world's next great video game. There was no video game. Jack Tramiel killed it in late November 1981, 3 weeks after the chips were finished, and decided they would go into a 64 kilobyte home computer instead, to be shown at CES in the second week of January. The machine's architecture was laid out on paper in 2 days. 5 working prototypes existed before New Year 1982. At the show, according to a Commodore engineer, all we saw at our booth were Atari people with their mouths dropping open saying, "How can you do that for $595? Yanez on what that cost him. The issue wasn't budget, it was development time and chip size constraints. The schedule was incredibly tight, some would say impossibly tight. And on the architecture itself, it's pretty brute force. I didn't have time to be elegant. What he got into the silicon anyway is remarkable. 3 voices, each with a 24-bit phase accumulator, 4 waveforms, a hardware ADSR envelope, ring modulation, oscillator sync, variable pulse width, an external audio input, and a state variable multi-mode analog filter with programmable cutoff and resonance. The competition in 1982 was the Atari Pokey, the General Instrument AY38910, the Texas Instruments SN76489, square waves noise of volume register, no envelope hardware, no filter of any kind. The SID gave a mass-market home computer the feature list of a monophonic analog synthesizer voice 3 times over for $4 of bill of materials. And the filter is where it falls apart. Yanez, 1996, and this is the sentence the whole episode turns on. The filter is the worst part of SID because I could not create high-gain op-amps in NMOS, which were essential to a resonant filter. In addition, the resistance of the FETs varied considerably with processing. So different lots of SID chips had different cutoff frequency characteristics. Then, I knew it wouldn't work very well, but it was better than nothing, and I didn't have time to make it better. He said it more starkly to IEEE Spectrum in 1985. The filter was the last thing that was worked on. I ran out of time. The simulation said, this will not work very well. And it didn't. He had simulation output telling him the filter would fall short, and shipped anyway. The whole chip had taken 9 months. The managerial view via Brian Bagnall's history from Charles Winterbull. This thing is already 10 times better than anything out there and 20 times better than it needs to be. Both men were right, which is why the decision was easy. The spec sheet went wrong too. Yanez wrote it before prototypes existed. It was then, in his words, distributed and copied and rewritten by various people until it made practically no sense anymore. The filter equations in it were simply wrong. They didn't hang together. No one gave me a chance to correct them. He told the consequence twice, 11 years apart. Games arrived from Japanese studios, written correctly against the spec sheet, producing sounds that were out of tune or inaudible. His account. Rather than correct the obvious errors in their code, they produced games with out-of-tune sounds and filter settings that produced only quiet, muffled sound at the output. As far as they were concerned, it didn't matter that their code sounded all wrong. They had written their code correctly according to the spec, and that was all that mattered. The engineering reasons the filter drifted are worth having precisely. It is an analog block on a digital MOS process. No variable transconductance amplifier was available, so FETs were pressed into service as voltage-controlled resistors, and FET resistance varies with process. The masks were deliberately laid out at 7 micrometers when the state-of-the-art was 6 to improve yield. Yield-first choices on an analog block widen the parametric spread. The cutoff control is an 11-bit converter, except it isn't. Yanez, it's actually a 12-bit D to A, but the least significant bit had no audible effect, so I disconnected it. And on the board, the sound output traces run alongside the video traces. Part of the Commodore 64's audible whine is not the chip at all, it is the layout. The envelope has a quirk of its own. The rate counter is reset only when it matches its comparison value, not when the envelope changes phase. So a fast phase following a slow one has to run the counter all the way up and wrap around before it matches. Worst case, about 33 milliseconds of nothing before the note starts. Musicians worked around it by writing zeros to the envelope registers and holding for 2 frames before every note to force the counters into a known state. It is called a hard restart, and it is why so much Commodore 64 music has a tiny percussive tick at the front of each note. The workaround became the timbre. Martin Galway, who wrote music for Whizball and Arkanoid and the Ocean Loaders, described the bug in his own vocabulary, without knowing the register-level cause. He called it the school band effect. The second exploit is better, because Yanez describes the defect and the exploit in the same breath. The final amplifier was a 4-bit multiplying converter. His words, by stopping an oscillator, it was possible to apply a DC voltage to this D to A. Audio could then be created by having the microprocessor write the final volume register in real time. Game programs often use this method to synthesize speech or play sampled sounds. And earlier in the same interview, listing what he would have fixed with more time. A proper op-amp, which would have eliminated the signal leakage which occurred when the volume of the voice was supposed to be 0. That leakage is the DC offset. The thing he would have removed is the thing that gave the Commodore 64 sampled drums and speech. There are more. Combined waveforms were possible only because there was no silicon for an interlock to prevent them, and Yanez discouraged using them because they could lock up the noise generator by filling it with zeros. Composers used them anyway, for timbres. And the readback register he predicted was probably never used became the machine's standard hardware random number generator. 3 oscillators and you need bass, melody, and harmony. So composers cycled one voice rapidly through chord tones to fake a chord. That arpeggio is the single most recognizable sound in video game music, and it exists because there was no 4th voice. In 1987, Commodore shipped the 8580. Different process, 9 volts instead of 12, different filter capacitors. The cutoff response is linear and consistent. Resonance works properly, the distortion is gone, the DC offset is gone. Wikipedia's summary of Commodore's own change is exact and damning. It was revised to more closely match the specifications. Musicians said it sounded thin. They were right. And the reason is that every improvement was the removal of an artifact they had been composing with. The 6581's signal-dependent cutoff modulation was doing timbral work. Filter sweeps, written against its nonlinearity, now land in the wrong place. the volume register samples stop working entirely. The 8580 is not the worst chip. The two are mutually incompatible instruments sharing a pinout. The 8580 is the chip the datasheet always described, and it is the one nobody wanted. The specification was wrong about the instrument. A decade later, Electron built a commercial synthesizer around a real 6581, specifically revision R4AR, described as the best trade-off between sound, stability, and conformity, a product choosing the defective revision on purpose. Which brings us to why this chip cannot be emulated. DAG Lim's RE-SID is cycle accurate and implements a proper 2-integrator biquad filter. Its documented weakness is precisely that its filters are linear, and so do not reproduce the 6581's nonlinearity. Accuracy only improved when Antti Lankila began simulating the distortion in 2007, working from measurements of real chips and from decapped die photography. The research program had to change its question from what was this supposed to do to what does this particular piece of silicon actually do wrong. The modern replacement chips make the point unanswerable. Sidekick Pico ships a library of per-chip filter presets derived from measurements of individual real 6581s, with the limits left user-adjustable. Its flagship feature is a menu of different manufacturing defects. You cannot ship one 6581 emulation because there was never one 6581. Every chip is a slightly different instrument. The serial number is part of the timbre. Yanez left Commodore in spring 1983 and co-founded Ensoniq, where he built the Mirage sampler and a chip with 32 time-multiplexed oscillators that Apple licensed for the 2GS. The SID is often described as growing up into that chip. Yanez says otherwise. All Ensoniq sound chips use a multiplexed oscillator. Aside from that, little else of SID is to be found in our designs, which more closely resemble the Mountain Computer sound card for the Apple II. What he inherited from the SID was a negative lesson learned under deadline on multiplexed oscillators waste die area. In 1996, an interviewer asked him whether he had heard the music. Rob Hubbard, Martin Galway, Jerome Tell. His answer, I'm afraid not. Are recordings available in the US? Asked what the SID had meant for his industry, he said, well, I don't think it had much impact on the synthesizer industry. He was right about that, and it is the least interesting thing about the chip. It had no impact on synthesizers. It had 4 decades of impact on everyone who could only afford a computer.